Hello and welcome to Everything. This is Every Astronomical Object. So let us define our terms. What counts as an astronomical object? Well, I'm going to use the Wikipedia definition because it's good enough. A naturally occurring physical entity, association, or structure that exists in the observable universe. So I'm going to split this out into three broad categories. First of all, stars as our basis point. We'll look at different spectral classes, definition between dwarf and giant stars, variable stars, protostars, and stellar remnants, etc. Then I'll look at things that are smaller than stars, like planets, moons, asteroids, etc. Then finally, I'll wrap up with things that are bigger than stars, like systems, galaxies, superstructure, and the like. And then just a quick key here. If you see text in green, that means I'll be covering them in more detail in a later slide. If you see a purple text, that means I've already covered it in a previous slide, so I'll just brief over it. And then red text means it's a hypothetical object. Okay, then let's get started with stars. So stars can be defined most broadly using what's called the Hertzsprung-Russell diagram. It tracks spectral type, aka temperature, on one axis and luminosity on the other, so how bright it appears, or how bright it actually is. There is a difference between apparent and absolute magnitude. So this shows the absolute magnitude. And you can see there's a variety of different spectral types there's O, B, A, F, G, K, M, L, T in decreasing temperatures. So O's are the hottest, the blues, and then T's are the coolest, the reds, or lower. And through each of these, there's actually, at the low end, there's also hypothetically maybe a Y type, which is like really cool brown dwarfs. And each of these divisions, spectral classes, can be subdivided from 0 to 9. For example, the sun is a G2 star. Now, there might not actually be subdivisions of the O's of 0 and 1. Those would be really, really hot. The lower the number, the hotter, so they might be hypothetical, but every other sort of subdivision should exist. So we talked about spectral class and luminosity, and you can see they're separated down into a lot of different sort of conceptual groups. The biggest one here is the main sequence, aka dwarf stars. For historical reasons, normal sized stars that we think of, including our sun, are actually dwarf stars, and anything bigger is a giant. So you have lots of different types of giants, which we'll cover in more detail later, as well as dwarfs of different types we'll cover later. Now, just to give you an example of each spectral class or spectral type, I have shown out here. So number 3 here, that is the HD 269810. That is an O-class star. There's the Jewel Blocks cluster here, which are B-type stars. This is Vega, a A-type star. This is Canopus, a F-type star. Our sun, which is a G star. Sigma Draconis, a K star. Betelgeuse is an M star, and then these are conceptual images of a L-type dwarf and a T-type dwarf. Okay. So I talked about dwarf stars. Most main sequence stars are, in fact, dwarf stars. So there's hypothetically there could be blue dwarfs, but I don't think any of them have actually been observed. Now yellow dwarfs are masses compared to a sun, so our sun is a yellow dwarf. There are orange dwarfs; those are K-type main sequence stars. Again, kind of referencing this, you can see the color. Makes sense that these would be orange, yellow is this band here. Again on this main sequence. Reds are going to be low mass main sequence stars around here, and then brown is substellar. They're actually not technically stars, or I don't know, there's inconsistency, or depending on how you define your terms. But anyways, they can't fuse hydrogen into helium, kind of the main property of how stars produce energy. They can actually, though, fuse deuterium, which is hydrogen too. So they still have some fusion activity. And then there's these subdwarfs, where actually below the main sequence. Here's an example here of Capitoline star. You can see it's a lot smaller than the sun, but it's still bigger than the Earth or even Jupiter. So it's a rather small star. And there's different classes between the subdwarfs. There's cool. They can either be cool, extremely cool, or ultra cool. And then it can be hot dwarfs and then heavy metal dwarfs, which sounds like a sweet band name. On the other side of the coin, we have the giants. There's a couple different classes. So there's like subgiants that kind of fall below size and luminosity, nearest to the main sequence. An example of that would be 17 here. Gamma Geminorium, it's an A-type subgiant. And then a proper red giant. So red giants are the state of late stellar evolution. So most main sequence stars, normal sized stars, develop into red giants when they get old, like our sun will. There's different kinds. There's the red giant branch. They're still fusing hydrogen into helium in a shell surrounded in an inert helium core. The red clump group are a cool half of the horizontal branch where there's helium fusing in the core and then hydrogen in a shell. And then the asymptotic giant branch, there's an inert carbon-oxygen core, a helium shell, and another hydrogen shell. And that's shown here by 18. That is Arcturus. Now, there are, again, just with like the dwarfs, different colors. There's yellow giants. Those are intermediate stages of larger stars, often pretty variable, or they vary in luminosity. We'll explain variable stars later. But here is Capella. So the AA, that's this one here, that is a yellow giant. There can be blue or white giants. They may be high mass stars or lower mass stars under specific conditions. And the example I have here is Alcyon. It's Eta Tau, also known as Eta Tau. It's a blue giant. I think it's in this red circle here. Okay, then there's bright giants. They're kind of between normal and super giants. And we've already seen this. Canobus is actually a bright giant. Then there's supergiants, extra large stars. One of the subtypes of that is Wolf-Rayet stars. They have unusual spectra. They have massive stars that lost helium and are lost hydrogen and are fusing helium. They have a sun-like in the center of a nebula with a bare carbon-oxygen core. So here's an example of a WR124 Wolf-Rayet star. There's also some other types like still on the asymptotic giant branch are these BE stars. Then red supergiants are some of the largest stars. Some of the largest stars become red supergiants, though they're not the most massive or bright. They're rather cool. So an example would be, we've already seen Betelgeuse. That is a red supergiant. And then there's hypergiants. They're very rare, really not well defined, except for yellow hypergiants are more well defined, and should see those later. And here's kind of an example here of just hypergiants in general. On the right side here we have VY Canis Majoris. It's a hypergiant compared to other size stars. You can see it's quite a bit larger. And then here is IRAS 17163-3907. It is a yellow hypergiant. Now that we've parsed out stars by color, temperature, luminosity, size, we're going to go into what are called variable stars, so how they change over time. So variable stars, it means the brightness, their luminosity, how they appear on Earth, changes over time. Some will periodically dim or brighten on different cycles, and these are actually really important for the history of astronomy. So the most important one, so we'll start with pulsating ones. The most important ones here are Cepheid or Cepheid-like variables. They pulsate rapidly with a very well-defined period and amplitude, so this luminosity and pulsation actually can be used as a benchmark because they often are found in groups of other stars all at the same distance away. And if you can know that a star is a Cepheid variable. They have a very specific luminosity based on the pulsation, so you can get the true luminosity, not just the apparent luminosity, because obviously a star that is farther away looks dimmer, even though it might be very bright, and so you can use that as what they call a standard candle to get true astronomical distances to different parts of the universe. And there's various types. There's type 1, these are classical or the Delta Scuti. They are giants with periods on days to months. There's type 2, with their metal poor, they have low mass stars, 1 to 50 day periods. So specifically the Delta Scuti, these are young pulsating stars. And then for a next group on the Cepheids, there's the RR Lyrae. They're periodic. They're found in globular clusters. They're horizontal red stars about 1/2 the sun's mass. There's rapidly oscillating AP stars. P is for peculiar. They're essentially A or B stars with extra metals, and they have rapid pulses in the order of minutes. Then there's XX Phonesis. These have short periods of an hour or two, and they're low metal stars. And a lot of times these stars, like W Virginius, BL Hercules, RV Tauri, these are special because of type 2, etc. Are Lyrae. They're usually based off of like the first star that was discovered with these properties. That's why they sound like an individual star. So there's both a star class and then the actual individual star that it goes underneath. Okay, kind of going more into these blue-white with early spectra. So we have Alpha Cygni. It's a variable with non-radial pulsations. Beta Cephei, small rapid variations. These are hot blue-white stars. There's slowly pulsating B types. They're long periods, half to 5 days. Their main sequence stars are 3 to 9 times the size of the sun. And then the PV Telescopi, these have long periods. Or sorry, not long periods, but they're small but complex radial velocity fluctuations. And these are helium supergiants, BP stars. And then there's the blue large amplitude pulsars, or pulsators. Pulsars are a different thing. Pulsators, they're very rare, only about 14 I think have been discovered, and they have large amplitude and short period. Now under the long period, the most common ones are the most known ones are the Mira. These are late stage red giants with periods greater than 100 days. There's semi-regular stars, which are cooler giants or supergiants with irregular periods, and then slower regulars, slowly changing light with little or no real periodicity, and there's different types. There's like A, B, and C. Over on the other types of pulsating stars, there's Gamma Doradus. They have variations due to non-radial pulsations. They're solar-like, so one's oscillators that oscillate the same as the sun due to like turbulent convection of outer layers. And then there's things like that are called pulsating white dwarfs. We'll go more into what white dwarfs are later, but there's different kinds. DAV, DBV, GWVer, DQV, and ELMV. And they're white dwarfs that pulsate due to radiogravity wave. Another type of variable star is the eruptive type. So first of all, there are protostars or pre-main sequence stars. We'll go more into that detail later with stellar beginnings. But there's different kinds. There's the Herbig AEBE. These have protostars with gravitational contraction. They're not burning hydrogen yet, and so they have variation. There's Orions. They're irregular and eruptive variation. Their luminosity is typically associated with diffuse nebulae. We'll talk about what nebulae are too. And there's some subtypes. There's FU Orionis. These have extreme changes in magnitude and spectral type. They flare with a mass transfer, probably from an accretion disk to a young low-mass T Tauri star. And then T Tauri, they're very young stars. They're not burning hydrogen yet. They occur mostly in binaries. They have spectral lines with singularly ionized iron. And there's different kinds. There's classical, weak line, and naked. And here's a picture here of a T Tauri impression of this young star forming. Okay, other types of stars. We've already seen giants and supergiants, but Some of them are important eruptive variables. There's the luminous blue variables. They're massive evolved stars with unpredictable and dramatic variation. These are pretty rare, only about 20 have been found. There's R Coronae Borealis. These are, again, varies in luminosity, but in two modes, a low amplitude pulse and an irregular sudden fade, and there's about 150 of these. Then there is DY Persei, that's a subtype of the Borealis. These are carbon-rich asymptotic giant branch stars, similar to, again, the R Coronae Borealis. Then there's yellow hypergiants. We talked about this before, but they're cooler than the luminous blue variables. Okay, and we see Canis Majoris 30 here. That is AG Carinae. That is one of the luminous blue variables. Okay, so then there's eruptive binaries. There's double periodic. They vary due to eclipses and another cycle. So there might be some mass transfer going on between two stars. Then Canis Majoris, these are very poorly understood, and here shows a light curve here of Canis Majoris. They're poorly understood. They're a B-type star with a dust envelope and probably a mass transfer to another star or stellar object. Then there is RS Canum Venaticorum. These are close binary stars, so two stars with an active chromospheres, so large stellar spots that are happening. And then under the other category of eruptive stars, there's flare stars. They dramatically increase for a few minutes, kind of analogous to solar flares, and then go back down. I'm not sure if anyone really knows why yet. And there's Agana Cassiopeae. They have irregular changes on the time scale of decades. And here's an example of the namesake star Gamma Cassiopeae. You can see how it varies over time. Then there's Lambda Iridani. These are small amplitude variations, higher irregular, half day to 2 days. And then Wolf-Rayet star, we already saw that. And their separation from O-type stars is not obvious. So there's some that things called like slash stars straddle the line between O stars and Wolf-Rayet stars. Another class of variable stars are the cataclysmic. We'll start with AM Canum Venaticorum. These are rare hot blue binary variables where the white dwarf, so one of the variable stars is white dwarf, it accretes hydrogen poor matter from a compact companion, so maybe another white dwarf, and has periods less than an hour, and there might be gravitational waves going on there, and they lack hydrogen lines. Then there is the luminous red nova. It's a stellar explosion possibly caused by a merger of two stars and has a red color. So this is an example of possible luminous red nova, V838 Monocerotis. Now there's nova, which means new star. It's a transient event, sudden appearance of a new star that fades, quote unquote. A lot of them might be white dwarfs in close binary systems where there's a gravitational accretion. So here's the conception here. Gravitational accretion of like a subgiant or a red giant that builds up and causes runaway fusion, causing the change in luminosity. Different kinds. There's a classical. There's the dwarf, where a white dwarf accretes matter. It's dimmer and repeats more frequently than a classical nova. There's a polar, where there's a white dwarf and a red giant. Again, highly magnetic pulls matter. So the other two, classical and dwarf, it's gravitational, that through gravity that the accretion occurs. But in a polar, it's magnetic force that pulls the matter to the white dwarf. There also might be an intermediate between polar and regular. And I think I missed recurrent, so that just means it occurs more. Instead of just a one-time event, this nova type event occurs more than once. Then there's supernova, which we'll go into more detail later. But there can be supernova, hypernova. There's essentially an explosion of giant stars. Other types of cataclysmic variables, there's the SW6 Tantus. These are white dwarfs and a red giant, and then emission line from helium and hydrogen are not doubled. So again, almost all of these cataclysmic nova type stars are going to be binary systems where there's accretion of matter from one star to another. So there's a specific kind. And then there's the symbiotic, so again a white dwarf and a red giant. They have quiescent and active phases. And then there's a couple subtypes. There's symbiotic nova, like the classical nova, but very slow outbursts, can remain maxed for years. And then the Z Andromedae is another type, and I have an example here where you can see how there can be changes in how maxed out they are over time. Quiescent and then more active phases. We are not done with variable stars yet. There's a lot of different kinds, and they're very important for astronomy. So unsurprisingly, a lot of them have been named and described. So there's a rotating type now. There's a variety of different kinds, but within the rotating, there's the non-spherical and then the rotating ellipsoidal. This is where close binary systems move around with ellipsoidal movements. Some can be rotating, can be caused by stellar spots. So stars rotate. If they have spots in them, that won't be as bright, so it'll dim slightly. So there's BY Draconis. That the rotation of the star coupled with star spots. These are spectral class of K or M stars. There's the FK Cometae Berenices, and these have extremely rapid rotation. And so you can see the rapid rotation of the FK Cometae Berenices, and then up here, this is a type of a rotating ellipsoidal, the star Spica. See how there's, again, periodicity, just like all variable stars. And then some are caused by magnetic fields rotation. There's the alpha power 2 Canum Venatoricum. Here's an example here. And for these ones, the magnitude changes due to changes in the magnetic field of the star. Pulsars, same thing happened, but those are stellar remnants. We'll explain those more in detail. SX Arietis have high temperature. They're essentially high temperature analogs of alpha power 2 Canum Venatorium stars. Then there's eclipsing stars. Again, this is the most conceptually understandable binary star systems where one star will eclipse the other, causing a dip or increase in luminosity depending on the stars being eclipsed. So there's the angle. There are eclipsing binaries with well-defined start and ends, so they're both spherical. There's the Beta Lyrae. These are large stars with ellipsoidal shapes due to gravity distortion. There is planetary. So a planet eclipses the sun. So a planet passes between the star and the Earth, and there's a slight dip in luminosity. And this is actually how we discovered the first exoplanets, by looking very carefully about stars and whether they dipped in luminosity. And then there's the W Ursae Majoris. These are low mass contact binaries where the stars are actually physically contact. So this is a schematic of that star where the stars are actually, in a sense, not so much one is accreting solar material to another, but they're kind of combined, not exactly fused, but very, very close together. Okay, we've come to the end of our major stellar classification. Now let's turn to the beginning of stars, stellar beginnings. So first of all, most stars, newborn stars, forms in dense clouds of gas. These are sometimes called as stellar nurseries. There's also more defined explanations. There are what's called nebula. Nebula is a term that's used for several different objects in astronomy. There really just is a cloud of something. So here, the three main ones for stellar nurseries are H2 regions. These are large diffuse nebula. Then there's emission nebula. These are clouds of high temperature gas, usually the site of ongoing star formation. And then there's reflection nebula. Clouds of dust reflect nearby stars, again, usually sites of star formation. So 40 here is an emission nebula, NGC 2174. And then this is the Witch's Head reflection nebula. Okay, within stellar nurseries, there are protostars that can be ranked from classes 0 to 3. So these protostars form from molecular clouds called dense cores. The stars start to collapse and eventually fusion starts. The classes are based on peak emissions of radiation. So 0 is sub-millimeter, 1 is far infrared, 2 is near infrared, and 3 is visible. So you can't really see stars visibly until they get to 3. Then they kind of go to the pre-main sequence. We've already seen T Tauri, but these are young stars, less than 10 million years old. The youngest visible ones are going to be F, G, K, and M spectral types. And we've seen the T Tauri stars before. There's also the Herbig AEB stars. Again, we've seen before, they're embedded in gas dust envelopes. And here is an example. This is the Elephant's Trunk Nebula. The red kind of embedded in here are probably protostars. We've talked about stellar beginnings, so now let's talk about stellar ends, the fate of stars. So most small stars will end as a white dwarf. So as they go through their life, as on the main sequence, they eventually leave the main sequence, become giant stars, or like red giants. And depending on different characteristics, different things will happen. If they're by themselves, there's no other companion star. What usually happens is they eventually run out of essentially they run out of hydrogen to really fuse, to keep their cores from collapsing. So the cores collapse, and that pressure and heat lets them start fusing helium, and then that expands and they get bigger and cooler. And this will happen for several cycles. They can start to burn heavier and heavier elements. Again, it depends on the star size. So eventually they can't anymore, and their outer layers go out. Sometimes they become planetary nebula, and then you're left with a stellar core remnant. It's dense, no fusion, low mass star, and these stars are known as white dwarfs. The different kinds. There's a carbon-oxygen white dwarf. The usual one is composed of carbon and oxygen. There's a oxygen neon magnesium white star. These are smaller stars that start out with 8 to 10.5 solar mass. They can fuse carbon but not neon. And then there's a helium white dwarf. These are low mass stars that never burn helium at all. And then there's a hypothetical type of dwarf called a black dwarf that after a white dwarf cools long enough to the fact that it's like completely cooled at all and no heat left, be theoretically a black dwarf, but actually the age of the universe is still too young for any of these to actually have formed. But eventually, when their universe is old enough, there'll be black dwarfs that are cooled remnants of white dwarfs. And here's just an example of a white dwarf here, Sirius B. So I think this is Sirius A, but you see this little arrow and dot that's a very faint, these are very small stellar remnants, white dwarf. On to the more exciting end, supernova explosions. So the type 1A supernova is actually starts with a white dwarf in a binary system. We've kind of seen this schematic before. The white dwarf actually accretes matter from a companion star until a critical limit happens. There's a thermal runaway and an explosion that happens. There might be an alternative type where there's a merger of two white dwarfs. Now the rest of supernovas are typically the explosion through the collapse of a massive star, a very big star. Our sun's too small to do this. It needs to be much bigger stars. Type 1b and 1c, again, are going to be massive star collapses. And though most of their masses, they've lost most of their outer hydrogen before that happens. So I think a good example of this is 47 here. This is supernova 1987A. Now there's type 2 here, P and L. So P means, and these are massive star collapses, 8 to 40 or 50 mass of the sun. So these are very big stars. So the P and L difference is P has this plateau in light curve decline over time, where L does not. So that was what differentiates the two. Now the type 2N and type 2B, that means, so N means narrow, so they have narrow hydrogen emission lines, and then that might be due to an interaction with circumstellar medium. Where the type 2B has a weak hydrogen line. Later on, hydrogen emission line becomes undetectable and it has a second peak of a light curve similar to type 1B. That's why it's called 2B, kind of similar to 1B in some respects. Now then there's types 3, 4, and 5, which are sort of hypothetical. They're really based on like anomalous supernova that have been noted, and they're like, well, maybe this is a type of supernova we just don't have enough information on. So 3, an example of that would be supernova 1961I. It had an odd light curve. There's supernova NGC 3003. That also had a light curve, that odd light curve, that might be a 4. And then the supernova 1961V plus some other ones in this category 5 had a similarly odd light curve that didn't fit any of the other categories. Then there are hypernova. These are massive stars greater than 30 times the mass of the sun. These are going to be the largest blue supergiants. And when they have an explosion, they form rotating black holes with jets. And so they're essentially a really big type 1C. And this is an example here, I think pointing. This is hypernova SN 1998BW. And then there's another thing here called a gamma ray burst, which are really immensely energetic explosions. And though it's not clear what they are, they're probably supernova or something along those lines. Now, with supernova, that's not the end of the story. But before we get into what happens after supernova, what's left there, let's clear up a little bit things about nebulas, because they kind of fit in here too. We already looked at nebulas with stellar beginnings. So we looked at the H2 region emission reflection nebulas, but there's other types here that usually have to come in the form of stellar ends. So there are planetary nebulas. These are remnants of the final stage of stellar evolution for mid-sized stars. They're essentially shells made of the outer layers of the red giant phase with a white dwarf in the center. So example here is the Oyster Nebula. There's also protoplanetary. There's sort of a short-lived in between some of the giant branch phases. Then there's supernova remnants. So when supernovas blow up, that expanding shell of gas from a supernova can be visible. This is the Crab Nebula, probably the most famous supernova remnant. There's also dark nebula, aka absorption nebula, kind of in contrast with emission reflection nebula. These are so dense that it obscures lights from objects behind it. And small isolated types of dark nebulas are called Bok globules. In this example here, this is a dark nebula LDN 1768 or 1768. Another type of newer nebula is called the flux or the integrated flux nebula. It's a relatively new type, as I said. It's illuminated not by a single star, but the integrated flux of all stars in a galaxy. This is an example of an integrated flux around Polaris, the star Polaris. And finally, there's diffuse nebula. These are most nebula. They're extended to have no well-defined boundaries. Like some of these nebulas, you can really see the boundaries. Most of them are like this one here from the Carina Nebula, very diffuse. We were sidetracked a bit by nebula, but let's keep going with what happens after supernova. So, one thing that can happen after a supernova is a neutron star. This is a collapsed core of a massive supergiant star, 10 to 25 solar masses. is the smallest and densest object in the universe outside of black holes. So there's different types. There's type 1 and 2. These are by size. The type 1 are low mass and cooling rates. Type 2 is higher mass and cooling rates. And then hypothetically, there could be a type 3, which even higher mass and cooling rates. Now, a specific kind of neutron star, a very important kind, is a pulsar. This has a pulsating radio source. It emits beams of electromagnetic radiation out of magnetic poles, kind of like a lighthouse. You might have even seen animations where pulsar is pulsing around like a lighthouse. There's different kinds. There's rotation powered, where it's powered by the loss of rotation energy. There's accretion powered, gravitational energy of accreted matter. This produces X-rays. There's also magnetars, where it's the decay of an extremely strong magnetic field. And there's a disrupted recycled, where two massive stars in a binary system go supernova, and then the first pulsar forms and sucks off matter from the second, re-charging its magnetic field. There are non-pulsing neutron stars, and then also binary neutron star systems, which is about, actually, I think 5% of all neutron stars are in a binary system. And you can see through this picture here, this is an example of neutron star formation. You see a massive star collapses and leaves a neutron star, and then the different neutron star types, magnetar pulsars, and you can have both at the same time. On beyond neutron stars, in fact densest object in the universe is a black hole. These form when very massive stars, 25 or more times the solar mass of the sun, in most conditions, but not always, form. And so they're so compact that light can't escape its event horizon. So there's a couple different types, depending on size, properties, or etc. So by size, there's our stellar black holes. These are just collapses of massive stars. You can kind of see here the schematic. We have the event horizon, so if anything passes into that, it won't escape. There's a singularity at the middle, which sort of the laws of physics sort of break down, and how to tell whether you're in an event horizon or not is called the Schwarzschild radius. So in addition to stellar, there are supermassive black holes. These are found in the center of most galaxies. It's really unclear how they're formed. They might grow from absorbing surroundings or merging with other black holes, but almost all galaxies have them. Our galaxy has one, Sagittarius A star. And then there's intermediate mass ones. And these are in between stellar and supermassive, maybe again from the merging of smaller black holes or collision of massive stars, or they might even be primordial, so from kind of the earliest parts of the universe. There could also be micro black holes. These are hypothetical. Again, they could be primordial or from some other strange formation. So just before I move on, this is a actual photograph, and if you follow astronomy news at all, this is a pretty big deal. Recently, this was a picture of a black hole in the Messier 87 galaxy. And if you look in here, there's some black hole properties that might be important to talk about. There's, again, in the event horizon, there's usually an accretion disk if they're active, so this is material falling into the black hole. And then if the black hole is active in accretion matter, they usually have this thing called a jet or beam, a relatively jet that shoots out high energy. Okay, so now let's talk about the fact that there's different properties. So there can be a charged black holes, and then they can be rotating or not. And I already went through this, but they can have jets and beams depending on their active, if they're actively essentially having material fall into them or not. Now, a term here is important to understand is active galactic nuclei. These are essentially supermassive black holes at the center of galaxies that are actively having matter fall into them, or accreting matter. That's another way to put it. So a couple important kinds. There are quasars. These are extremely luminous active galactic nucleus powered by accreting matter, thousands of times actually the luminosity of a galaxy. So when we first discovered these, we were like, what the heck are these? So it turns out they're giant black holes spewing out matter because of their accretion of matter. Because like not everything, with all that matter going in and whatever timey-wimey things you want to say, that not all of it can go in, and so energy gets shot out. This isn't the time to try to piece that together. This is more of a list type of work, so I'm not going to try to parse out exactly what's going on with equations. Okay, sorry, I digress too much. There's different kinds. Here there's radio loud, radio quiet, depending on whether you have radio waves. There's broad absorption line ones, type 2, red, optically violent variables, which sounds like another great band name, and then weak emission line, active galactic nuclei. And then there's blazars, which if you think quasars are cool, blazars are essentially the same thing, but they have relative big jets nearly the speed of light, and then they're directly at the viewer, so they're not like obliquely a little bit off like most quasars. Blazars are like directly in our line, viewing it from Earth. So here's a rendering of the ULAS J1120 plus 0641 quasar. You can see how it kind of shoot out, and then this is a rendition of a blazar, so pointing right at us. And subtypes here are lac objects, so optically violent variables, which we saw that those are also quasars. We have run the gamut of stars, so let's zoom in to items that are smaller than stars. So first of all, let's kind of get our mind around what we can consider. So we're going to start with things that are most familiar with us, so things that we find in the solar system, so aka solar system bodies. We'll talk about planets, satellites, including moons and moonlets, etc. Dwarf planets, minor planets, including a bunch of things like asteroids, small solar system bodies, which can be centaurs or comets, trans-Neptunian objects, Plutoids, Kuiper belt objects, scatter disk objects. Some of these things mix and match together, and then finally meteoroids. You can see this is a nice schematic of solar system bodies. You can see planets are their own thing, but then satellites can kind of fall between multiple categories, like some trans-Neptunian objects are satellites and some aren't. All dwarf planets can be minor planets, but not all minor planets are dwarf planets, so some of this distinction gets a little confusing, but we'll try to go through everything in at least as much detail to get a feel for it. Okay, so let's start with planets in our solar system. There are a couple different types. There are gas giants, ice giants, terrestrial rocky, and then dwarf. We'll cover more detail later. And so here's an example of kind of cutaways of different types of planets between a gas giant, like Jupiter and Saturn, and then Uranus and Neptune, which are ice giants. So gas giants are mostly hydrogen and helium, sometimes called failed stars. They probably have a solid core, kind of shown here. And then ice giants are mostly heavier than hydrogen and helium, so like oxygen, carbon, neon, or nitrogen, etc. And they might have a solid core as well. And then while terrestrial planets are composed primarily of silica, rocks, and metals. So again, in our solar system here, we have the 4 terrestrial planets, Mercury, Venus, Earth, and Mars, the 2 gas giants, Jupiter and Saturn, and then the 2 ice giants, Uranus and Neptune. And you can see here, now there's a lot of agitation about whether Pluto is a planet or not. Currently, it's not described as a planet, so I'm just going to go with that. If you think it is a planet, great. Just consider it a terrestrial / rocky planet. Okay, so speaking of Pluto, let's talk about what's a dwarf planet. So a dwarf planet is, so first of all, a planet is an object that is in space that's big, large, a non-stellar object that's large enough to become rounded, but also is able to gravitationally dominate their neighborhood. So that's what a classical planet is. And so if a planet is rounded, but it doesn't actually gravitationally dominate their neighborhood, it's been dubbed a dwarf planet. That's why Pluto eventually was described a dwarf planet, because it doesn't gravitation dominate its neighborhood. So there's several of them. in our solar system. Right now, there's maybe 10 or so. So let's walk through them. First of all, there's Ceres, which is in the asteroid belt between the orbits of Mars and Jupiter. And then the rest are actually trans-Neptunian objects. So these are found out beyond Neptune most of the time. So there's Pluto, of course, found here. There's also Quaoar, Sedna, Orcus, Hemei. We kind of see these here. Eris, Makemake, Gong, and then possibly Salacia, and then 202 MS4. These are not, I think, for sure dwarf planets. The rest ones are more likely to be dwarf planets. They might be smaller, too small to even be a dwarf planet, but it's right now. Okay, so outside of dwarf planets, what else is there? Well, there are natural satellites, aka moons. They orbit planets, dwarf planets, or even actually other satellites. So that's what a moon is. So, like for example, our moon here. Now, a moonlet is a particularly small natural satellite. They're often, I think, found in ring systems. So this is Earhart right here. Let's see, you can show that. Right here, Earhart, that's actually found in Saturn's ring. Now, a minor planet, moon, is a moon that orbits a minor planet. So an example here is 243 Ida and its moon Dactyl. And then another thing that's small, sort of a natural satellite, is a ring system. So they're composed, a disk or a ring composed of solid material, dust, or moonlets. So here is a schematic of Saturn's rings. Okay, let's walk through the number of moons in our solar system. So this is for the actual planets. These are the moon number. There's Mercury and Venus has 0, Earth has 1 moon, Mars has 2, Jupiter and Saturn have 80 and 83 respectively, Uranus has 27, and Neptune has 14. Among dwarf planets, Pluto actually has 5, Tremea has 2. In fact, that's one of the reasons why Pluto was originally classified as a planet but then demoted, because when we first saw it, we're like, oh, it looked a lot bigger than it actually is, because we can only kind of see both Pluto and its major moon Charon kind of together, and we thought it was one thing. Anyways, Hemea has 2. All the other dwarf planets shown here have 1, and then there is actually probably 442 minor planets within the solar system. Again, minor planets being bigger than other solar system bodies like asteroids, but too small to be considered actual dwarf planets. Okay, if we want to look at all the moons by name, I'm not going to quite do that, but at least throw them up on the screen here. The first 2 are pretty easy. Earth's has the moon, aka Luna, and then Mars has Phobos and Dismos. When we get out to Jupiter, it gets pretty intense. There's again 80 moons. I have them all here. Some of them don't actually have names. They just have like S2003J19. Other ones have names. So the biggest ones I've shown here, these are actually what's called the Galilean moons, because they're big enough for Galileo to actually see them in a microscope. It goes Io, Europa, Ganymede, and Callisto, with Ganymede being the largest. And these are actually in size order. So there's Ganymede at the top here all the way down to S2003J12. With Saturn, again, it has a lot of moons here. Same sort of order, largest by Titan, all the way down to S2009 S1. So here's a selection of the moons here from left to right. There's Minmus, Enceladus, Tethys, Diane, Rhea. Titan is in the background here. Iapetus is in the top right. And then there's irregularly shaped Hyperion in the bottom right. And then some other small moons here. And there's a lot of moons. And then another important point with Saturn, because it has that big ring system, it has innumerable moonlets around it as well. Okay, it's a little easier to do Uranus here and Neptune. And here are some of the biggest moons for that. Uranus has Titanian, Oberon, Umbriel, Ariel, Miranda, all the way down to Cupid being the smallest. And so here is its 6 largest moons compared to their proper relative size and order. So this is little ones Puck, Miranda, Ariel, Umbriel, Titania, and Oberon. And then for Neptune, we have Triton all the way down to Hippocamp. And this is and Triton's kind of weird here. You can see this is a schema of Neptune. Triton is in a much different orbit. So it orbits like this, whereas most of the other moons go in this green like here. So that's kind of interesting. All right, and then for the moons of minor planets, again, showing this picture up again here, Pluto has Charon, which is the largest, but it also has Nix, Styx, Charybdis, and Hydra. Hanume has Hyake and Namaka. Quotar has Waywant. Makemake has MK2. Gonggong has Zanglu. Eris has Dysnomia. Orcus has Vanth. And Salacia has Ecteia. There we go. Okay, so let's move on to minor planets. So again, actually, so minor planet is a bit of an ambiguous term. Sometimes it means things that are just smaller than a dwarf planet, full stop, or smaller than a dwarf planet, but not all of the things smaller than a dwarf planet. Anyways, asteroids can kind of straddle the limit between that. They're, I guess, technically minor planets. They can be 1 meter to 1,000 kilometers, and there's over 1 million known in the solar system, so we obviously can't go through all of them. And there's actually a fascinating array of ways to describe asteroids, which we'll try to get into here. So, first of all, there's composition. You can have a C, M, or S type. C is for carbonaceous, M is for metallic, and S is for silicaceous. And so we have some different examples here. We have 253 Malthide, it's a C type, 21 Lutetia, which is an M type, and 433 Eros is an S type. You can also describe asteroids where they're found. For example, most of them are found in the asteroid belt between Mars and Jupiter. And this is the kind of a table of the largest asteroid belt objects. We see here our old friend, the dwarf planet Ceres, is in the asteroid belt. More ways to describe asteroids. One way is through families. They share similar orbital elements, like semi-major axis, eccentricity, orbital inclination. So the top families are Eos, Eunomia, Flora, Hungaria, Hygeia, Coronis, Nysa, Themis, and Vesta. But there's like 122 or so far, so a lot of different families. You can also describe them by spectral type based on emission spectrum, color, and sometimes albedo. So kind of like you do with stars, that we're looking at kind of different things. There's a lot of different ways to look at it. There's the Tholian system, kind of that uses just letters. The SMAS2 system, which uses letters and also short kind of acronyms. And this is a picture just of some of the orbital elements kind of split out into different types, like the different families, or the spectral type, like the main E, main B, main C, kind of shown here, but then also like Eos, which is like a family. Okay. Looking at other small solar system bodies or minor planets, whatever you want to call them. First of all, there are centaurs, which are objects that orbit between Jupiter and Neptune and cross orbits of one or more giant planets. These are all what kind of makes them different from, say, like Trojans or other types of things. They have very unstable objects, and their colors are based on apparent magnitude. There's 2 types, very red and blue, which you can kind of see. This is the scale here, example, where you have different centaurs based on their color. Okay, next thing we can consider are trans-Neptunian objects. These are any minor planet, any solar system body, whatever, that orbits at an average distance farther out than Neptune. As you can see, there's a lot of different kinds. There's a term that's kind of hypothetical, I don't know if it's really used anymore, is Any dwarf planets that are trans-Neptunian, called Plutoids, though I don't think that's really a valid term anymore. There's also Kuiper belt objects. So the Kuiper belt is a circumstellar disk in the outer solar system, sort of like an asteroid belt, but these things are more icy than asteroidy. These are icy objects. There's different kinds. There's the classical types that are sometimes known as cubanos, which is great. They have low eccentricity. There's resonant ones that these are trans-Neptunian objects that their mean motion orbital resonance, they resonate with Neptune. And so these include types like Neptune Trojans, Plutinos, which are different from Plutoids apparently, and others. Then there's, I think, let's see here. So here's an example of 48695 Akaroth. I believe this is a Kuiper belt object. And it's very interesting because it's sort of two objects fused together here. Okay, then there's what's called scattered disk objects. So the scattered disk is a distant circumstellar disk within the Kuiper belt or on the sort of edges of the Kuiper belt with small icy bodies. These have high orbital and eccentricities, and these are some of the coldest and most distant objects in the solar system found in this scattered disk. So an example of this, we've already seen this, but this is another picture of it in a different way, is the dwarf planet Eris and its moon Desmonius again. This is the largest scattered disk object. Now then, outside of trans-Neptunian objects, there are comets. These are icy bodies of ice. They're sometimes known as dirty snowballs, and they swing in and out of, or they swing away from and close to the sun. Once they get close to the sun, they warm up and release gases, and that has the comet's tail. Here's an example of a comet here. I believe this is Comet Ison. So there's a couple different kinds. There's short period ones, also known as Encke-type. Within that, the M-type are very short periods, and all the short periods of orbital periods less than 200 years. So Encke has very short periods. Jupiter-type ones or Jupiter family ones, they have periods less than 20 years and low inclinations. And then Halley-type have 20 to 200 year periods with an inclination from 0 to 90 degrees. And then long period ones range from 200 years to thousands or even millions of years. There might even be what's called like single use or single period comets. So they come in once and are never seen again because they have such long periods that they leave the solar system altogether. Then there are meteoroids. These are smaller rocky bodies, kind of wrapping up the smaller than stars here. Small rocky or metallic bodies. They are significantly smaller than asteroids. That's what makes them different. They're grain size to meteor size. And just to kind of clarify some terminology, a meteoroid is what's found in space. A meteor is when it's falling in the atmosphere, and then a meteorite is when what you collect off the Earth after it hits the ground. And then finally, kind of at the smallest levels below meteoroids, you can maybe have micrometeoroids or maybe just space dust. So these are small little particles. Okay, so we finished out with our solar system. Let's take a little gander at other places because obviously the universe is a very big place, and there are small things that are smaller than stars far beyond our solar system. So the biggest thing here is, of course, exoplanets. Now, of course, there's going to be moons, moonlets, dwarf planets, etc., all the way out there, but we're just going to focus on the ones that we can kind of directly observe in some way or speculate to some interesting detail beyond just saying, oh yeah, of course there are moons somewhere else. So exoplanets are any planet outside the solar system. There have been over 1,000, over 1,500 discovered so far. And there's definitely all the types we see in the solar system. We see those same types or subtypes, as well as other types as well that we don't see in our solar system. So among gas giants, one of the kind of subtypes we don't see here, and these are actually some of the first discovered through that transiting method, are hot Jupiters. These are large planets, gas giants that are close to stars and have high surface temperatures. So here's just a schematic example of different hot Jupiters that we've discovered. There's ice giants too, and then also a subtype called mini Neptunes. So these are less massive than Neptune. Here's a conceptual example here. These also sometimes are called gas dwarfs. There's another type. Obviously, there's terrestrial and rocky, but a type kind of straight on the line there is super Earths. So these are bigger than Earth. So example here, this is a super Earth Kepler 10b, but they are still substantially lower than these ice giants or even a mini Neptune. And then, of course, really the most interesting planets, at least from usually most people's view, especially searching for life on other planets, would be Earth size, ones that kind of fit what we think of as a habitable planet. So these are some examples of Earth-sized planets that have been discovered so far. Some other conceptual kind of types of planets that are out there or maybe out there. We have ocean planets, conceptually shown here. They might be a super Earth to mini Neptune range, essentially covered entirely by liquid water. There will also be carbon planets, which are ultra-dry, carbon-rich planets. Lava planets, these are super dense planets, larger than Earth, and have very close orbit to the sun. Think like bigger, hotter Mercuries. Some conceptual planets that haven't been directly observed but hypothesized. There's the Chthonian planets, which might be the script core of a gas giant. So you can kind of see the conceptual here that we think gas giants have rocky cores. Maybe all that gas gets stripped off and it just has this little rocky planet. Another idea would be conceptual planet as a Trojan planet, where it's a small co-orbital companion to larger planets. Think of something like a really big Jupiter has essentially a moon, but the moon is like Earth-sized and maybe has its own moons as well. Is that a planet, or would that be a Trojan planet? That's kind of the idea here. There's also planets around other things than just normal stars. There's a especially important one would be like a pulsar planet around an orbiting pulsar. So this is a conception of HD 209458b. Or sorry, that's the Clothian planet here. This is just a conception of a pulsar planet in general, and this is a conception of the last category, which is a rogue planet that is ripped from its star system, is drifting cold in the void. Now that we've finalized our look at things smaller than stars, we'll at last zoom out to the things that are bigger than stars. The first obvious thing to look at is star systems, and we've seen this. We've brought up the concept of binary stars quite a bit. That plays into a lot of important things like variable stars, even like supernova formation. Anyways, a star system is simply a small number of stars that orbit each other. So we've seen binary star systems before. This is an example here of the binary system HD 106906. You could have trinary systems where we have the Engel system, this trinary star system. And in fact, once you get to trinary systems and beyond, you can have what's called like hierarchical setups. So the example is here at 100 here, or this is HR 68119 hierarchical triple system schematic, where we have, I think it's a black hole, a small red star orbiting each other in the middle here, and then we have another star orbiting them. So you can see this hierarchy, they're not just all rotating equally. There's a hierarchy, and that can get pretty complicated and interesting. Of course, you can have quaternary systems. In fact, I think astronomers has discovered up into at least octenary, so 8 stars, an 8-star star system. And that, at least one example, is Gamma Cassiopeia. There's also a special type of star system called a trapezia. These are very young stars, very unstable system in stellar nurseries that usually fragment into more stable sub-star systems. Now, beyond a star system, you can, of course, have a planetary system. These are where non-stars orbit around a star or a system of stars. So the solar system, that's what we call home, but of course, most other stars probably have planets and other things orbiting around them. Here are some schematics of some setups of planetary systems discovered by the Kepler spacecraft that we know of so far. Beyond that, there can be bigger organizations of stars. There can be star clouds. They're large groups of many stars within a galaxy. They can be really spread out, and they often contain clusters within them. So this is the Scotum star cloud. And so getting into clusters, these are large groups of stars. There's two main kinds, globular and opaline. Of the globular, these are tight groups of 10,000 to millions of old stars or typically old stars that are gravitationally bound. A subtype is a superstar cluster, which even very large regions of recent star formation. It's kind of like a precursor to a globular cluster. So they're probably younger, and the superstar cluster goes into a globular cluster as it gets older. Then so let's see, do I have an example here? Yes, so this is the Messier 15 globular cluster. Then we have open clusters, much looser, more like hundreds of stars, and these usually are younger stars. The example here is the Pleiades open cluster, very famous set of stars. And then within the open cluster, there are embedded ones. They are very young stars encased in interstellar dust or gas. Could probably be similar to or the same as a nebula or that type of nebula. There's an intermediate type of star clusters, obviously similar to globular, similar to open, but not quite one or the other. We found them in the Andromeda galaxy, but not in the Milky Way so far. So we're not sure why that is, but there's that. And then a subtype is a faint fuzzies, which is the least formal sounding name of anything I've found in astronomy. These are found in lenticular galaxies. We'll explain lenticular in a little bit. But they're large size and they have a ring-like distribution. They seem to be really old objects. So speaking of galaxies, let's get to galaxies. So galaxies are systems of astronomical objects, stars, planets, etc., mostly stars, bound together by gravity. There's several different types. The big ones are elliptical and spirals. Elliptical, also known as type E. They have elliptical shapes and very smooth features. You can't really determine much out of it. These are some examples here. And they go from E0 to be nearly spherical all the way to E7, which is highly elongated. Subtypes are supergiant. These are the largest ones, also known as type CD. There can be shell ones that are elliptical, where the stars in the halo are arranged in concentric shells. Then there's the spiral galaxy, which the Milky Way is a spiral galaxy. They resemble spiraling pinwheels. There's different types here. You can see, in some ways, in some setups, the Hubble diagram or the Valkaloris diagram just has two spirals and barred, but this one has an intermediate arm. The earlier one was with just two times, was called the tuning fork. I guess we can call this the fork model. Anyways, under regular ones, spirals, there can be type SA and A, B, or C. And the A, B, and C, they're different degrees of tightness from tightly wound over at A, with open, tightly wound all the way to well-defined arms at C. And then D, actually there's a D class too that you can add there, which means it's they're broken up and starting to be irregular. The intermediate, again, type SAB, so same characteristics as the regular, but just in between that and the barred. And the barred is called type SB, and same characteristics as you go out, they become, the winding becomes less tightly wound with less well-defined arms. But then the barred, of course, is different from a spiral because they have this bar in the middle and spirals don't. One other type is a superluminous spiral galaxy. It's very large with a high star formation rate. Other galaxies that kind of don't quite fit, we have lenticular. We've talked about before, also known as SO, and they can be type A or type B, depending on if they're more barred or more just regular spiral. They have a central bulge surrounded by extended disc-like structure, but no visible spiral structure. They almost look like they're kind of between elliptical and spiral. There's ring galaxies, as it shows an example here. It's called Huygens object. They have a ring-like appearance, and they're just the good old-fashioned irregular, both type 1 and type 2. They can't be really classified as anything else. They don't have a strong structure. LR1 has some of the structure that you could maybe fit kind of near the end here, but like type 2 has no structure that fits. Then there's an ultra diffuse ones that are really low density, very low visible star count, and these are probably all old stars. And there's another way to classify the dwarf galaxy. So most galaxies are actually dwarf galaxies, just sort of like how most stars are probably dwarf stars. And then dwarf can be the common type of other stars, so then there'd be a dwarf spiral, elliptical, irregular, etc. But then there's a very special type of a dwarf spheroidal, because small ellipticals don't really look like large. So dwarf elliptical stars don't always look like large elliptical galaxies. Elliptical galaxies. So, and here's an example of a dwarf spheroidal galaxy. Other important bits and pieces of galaxies are there's interacting galaxies where two or more galaxies are interacting in some way. So galaxies can kind of travel past each other and have a near miss and like warp each other a little bit, or they can directly collide while passing through and even, in fact, merge. So example, this is the antennae galaxies colliding, shown here. There's a thing called a starburst galaxy. Those are galaxies that form stars at an exceptional rate. They only last for a comparatively brief period of time from a cosmological scale, about 10 million years. Here's an example of a starburst galaxy. This is the M82. There are radio galaxies, which galaxies have giant regions of radio emission extending beyond the visible structure that you can see with your naked eye, or not so much naked eyes, but see with optical instruments. And the radio lobes are powered by jets from active galactic nuclei, so the supermassive black holes we talked about. So there's two different types, FR1 class and FR2 class. FR1 have low luminosity scores with what we call plumes. So this is an example here. There's jets with these plumes. Whereas FR2 are the most common kind. They have large-scale structures called lobes. And there's an example here. You see they're much more loby than the plumes. And you can have giant elliptical or giant radio galaxies when radio emissions extend to huge scales like megaparsecs, over 3 million light years long. Another important type is active galaxies. That's where their active galactic nuclei is. The supermassive black hole is accreting matter. We've already talked about quasars and blazars. There's also LINARs, which are low ionization nuclear emission-like regions. They have spectral line emissions that include weakly ionized or neutral atoms. It's unclear what powers this, but they're important and pretty common type of galaxy. For example, here is the Sombrero galaxy, which is a LINAR galaxy. Then there's the Seyfert galaxy, one of the larger groups of active galaxies. They have quasar-like nuclei. They're luminous and powered, but then their host galaxies are detectable. So usually you think of quasars or blazars as you only see the black hole being active, but you can't really see the fact that there's a whole galaxy around it. But with Seyfert, you can. And so the example here is, what is it? NGC6814. This is Seyfert galaxy, and there's different types. Type 1 is very bright, sources of UV and X-rays. Type 2 is bright core, especially at the infrared. And others are based on there's other types based on spectrum emission. Then finally, there is a luminous infrared. They have high luminosities in the infrared, and there's usually young stars around a surrounding dust. And then there can be ultraluminous, even brighter. These are fairly uncommon galaxies, but they were more common in earlier ages, and this is an example of IRAS 14348-1447. This is an ultraluminous infrared galaxy. If this were a Dr. Seuss book, I would be now calling this section On Beyond Galaxies. Let's talk about some superstructure. So, beyond galaxies, you can have a galaxy group, which is a group around 50 or so galaxies gravitationally bound together. Even bigger than that, we have a galaxy cluster, hundreds to thousands of galaxies bound by gravity. And then, of course, a supercluster, even bigger, basically one of the largest known structures in the universe. The Milky Way is part of a supercluster known as a local group. And here's an example of a galaxy cluster IDCS J1426. And there's also possibly even something even bigger than a supercluster, a hypercluster. So there we go. Then kind of beyond that, we have filaments. Filaments are the largest known structures in the universe. These are walls of gravitationally bound galaxy superclusters. So they're like things made up of their subcomponents are superclusters. They can have thread-like formations that form boundaries between large voids. So some different ways of saying things. There are galaxy walls. They have a greater maximum axis than minor axis in a cross section. So they're wall-shaped, as opposed to just regular filaments that are pretty narrow, kind of equally narrow cross section. And then sheets would be even thinner, like sheet-shaped. There's also something called large quasar groups, might be precursors to other clusters, etc. And then there's supercluster complexes, which is groups of superclusters, not so much with the shapes like filaments or walls, but just without a definitive shape. They're just kind of grouped together. We can see here, this is an example of the Sloan Great Wall, I think over here, and then this big one here I tried to blow up as much as I can. Some of the superstructures nearest Earth. You can see here that there's different walls we talked about. There is superclusters all over, and then things called voids. So let's talk about voids here. That is essentially vast spaces between filaments with little or no galaxies, just like empty space. And here's a conceptual idea of universe with the matter and void, sort of like this foamy setup where the colored stuff is the superstructure and then the black is the void. Okay, we're not quite done yet. I want to bring up just a couple more concepts that actually are important when we talk about very big structure. First of all is the cosmic microwave background. This is electromagnetic radiation remnant from the early stages of the universe, and it fills all of space, and we actually have kind of a picture of it here. So this is the radiation that left over from early stages of the universe. Now, the observable universe is everything we can see, but that's not probably all, almost certainly not all of the universe. That's only the universe we can see. There's an edge to it, because everything we can see has had to have enough time, like light, the radiation needs to have time to reach Earth for us to see it, and so we can look back almost to the beginning of the universe, billions of years back. But if things started out too far away, they haven't been able to reach us, so we can't actually see that. And it's actually worse than that, because the universe is expanding, and so there's actually some of the distant parts that we'll never see because they're expanding too far away, and things that we see now at the very edge of our limits that are going to pass beyond us, because space, light can't travel faster than light, but the space between regions, space between matter, can expand faster than the speed of light, so they can drop off of horizon. So there's all this stuff outside of what you even can see that the universe is. And that's sort of a fascinating thing to think about. But it gets more interesting than that, and I'm sure if you know anything about sort of introductory astronomy, you've probably heard of dark matter and dark energy. Because it turns out, of the matter we can actually see, that's actually a minority of the matter. About 85% of the matter in the universe is hypothesized to be dark matter. And it doesn't interact with electromagnetic radiation, therefore we can't see it. It's dark. But it seems to exist for a variety of reasons. One of the in observation and astronomy. Example, galaxies appear to rotate if they had a lot more mass than we can actually see. So unless something really has to change with physics, there's all this hidden matter that we know should be there, but we can't really detect. And if you saw my slog through my every particle, that was some of the things that talked about particles that might be dark matter candidates. But then it gets even crazier than that, because there's a thing called dark energy, which is an unknown form of energy that affects the universe on the largest scale, and that's actually behind the reason why the universe's expansion is actually accelerating. And it makes up about 72% of the total energy in the universe. So of everything in the universe, dark energy is like 3/4 of it. Of that, most of the other 1/4 is dark matter, and then just a tiny little slice of that is going to be the things that we can see and interact with. So everything we talked about here, stars, planets, galaxies, etc., are all just a little slice of a much larger universe that is sort of opaque to us. And that is mysterious and terribly exciting. With that, that is every astronomical object, subject, of course, to my own error, and new discoveries forthcoming. Hope you enjoyed. Brace yourselves for awesome and hopefully not a Type 2 supernova in the near future.